Okay, so we defined the linear basis model, linear basis function models. Then we have some parameters there, W. Okay, and then we have to define the loss function to train. Okay, so without the loss function or objective function, we don't know what to do. So the loss function is actually defining the direction of learning. Okay. And the given observed input x and the target t, then we can simply minimize errors defined by this. So this will be our loss function. So we want to minimize this one, which means by updating this parameter w, okay, let's assume that this nonlinear function is given. We can use Gaussian functions or sigmoidal or polynomials from the previous slide. So this one is fixed and xn is given and tn is given. So w is the parameter that we have to train. Okay, so by updating this w, then we want to minimize these errors. Okay, so look at this part. So tn minus, this one is our regression function. Then the difference between this tn and our estimation should be minimized. Okay, so that's what this loss function says. Okay, so is it just heuristic objective functions? It makes sense, right? But is it just heuristic? No, it is. It can be obtained by the maximum likelihood with the Gaussian noise model. Okay, so based on the probabilistic model, we can drive this equation. We can drive this loss function. Let's assume that observations are from a deterministic function and added Gaussian noise, like this. Which means this target label is generated based on these functions and the Gaussian noise. Okay, so when we observe the data, then we have x and we have a t. Okay, then let's assume that these labels are coming from a deterministic function with a noise. Okay, so this is kind of the true function which is unknown to us. Okay, we assume this, and P of epsilon is a Gaussian distribution. As always, most of the time, the noise will be modeled by as Gaussian distribution. Okay, because it's not interesting signal. And when we have these equations, which is equivalent to saying this. Probability of t given x and w and beta is actually 1 over variance. Okay, it's precision. Okay, so given x and w and beta. So x is input, which is given. Okay, w is parameter. We have to update. But in this case, if it is given, okay, now we're going to talk about how to update the w later. So if this is given, and when we add this Gaussian noise in this equation, we assume we actually provide these precisions. Okay, but we can train that too. Okay, so if all these are given, then what is the probability of the label t? Okay, that is a Gaussian, because this function is deterministic and it can define the mean of this t. Okay, and then uncertainty is given by this epsilon noise. Okay, this one uncertainty is coming from this epsilon directly, and the mean is coming from this deterministic function directly, because mean of epsilon is 0. Okay, so the t is coming from this Gaussian distribution where the mean is this function and variance is this. Okay, now we have a probabilistic model of these labels. Then given observed input x and the target t, then the likelihood function is given by this. So we already talked about this likelihood of a single input x and t. Okay, then when we have n samples, then we have to multiply. We have a product because we assume that the samples are IID. Okay, so most of the time in pattern recognition, so we assume that. Then we just multiply this Gaussian distribution n times. Okay, so basically the same equation here. So now we have a likelihood function. We usually take the logarithm. Okay, so we take a log, and then this is a summation and the log Gaussian. And we have another assumption here. So y of x omega is a linear. So we're still talking about the linear regressions with the nonlinear function. So this is our linear functions. Instead of y in the previous slide, then we have a linear equation here. So if we drive, the Gaussian distribution, the equation of Gaussian distribution. So if you apply the log function, then we have this constant with respect to w. So they have nothing to do with w, and we have this term. This term is coming from the exponential functions in the Gaussian distribution, and we want to maximize this log likelihood. Okay, then which means we have to minimize this part. Okay, because we have a minus signal here, so we have to this error, which is it's maximizing the log likelihood. That is, maximizing the log likelihood is minimizing residual sum of squares. Okay, so we got this equation. Okay, then to find the maximum likelihood estimate for w, then what should we do? So basically, take the derivative of the likelihood with respect to w. So let's try. Then from the previous slide here, we have w only here. This part is kind of constant. So let's take a derivative. Then we have beta and phi and this difference. Okay. Then we put the equation in the matrix notations. Y is phi w. If we have one sample, okay, then y is phi x transpose w, right? Then this one is a vector and the w is vector 2, so y is simply phi 0 x, phi 1 x, and phi m x times w1, w2, and wm. Okay, this is equation of one sample. Then when we have n samples, then y1 is phi 0x1 and phi 1x1, etc. phi m and x1 and w1 to wm, and y2 is phi 0x2 and phi 1x2 and phi mx2, etc. So we can just simply use a matrix form with this vector. Okay, this is what this equation says. Okay, then this equation can be rewritten with this matrix notation. And using the matrix notation to set the derivative to 0, okay, this should be 0, because this is the derivative of maximum likelihood. And based on this equation, then we can get these solutions. We can just move this term here. Okay, now we got this one. Then we need this one, right? So if this term is invertible, then we are happy. So maximum likelihood for W is given by this. So look at this one. And we multiply inverse is transpose phi inverse transpose t. So this term will be cancelled, and now we have this one. So this one has a special name, pseudo inverse. Okay. Also, we can get this maximum likelihood for beta. So if we treat this one as a parameter, then we can learn this one too from this. Okay. Then simply this variance can be obtained by this. Okay. So now let's get back to the simplest linear regressions. So in this case, we don't have a nonlinear basis function. So instead, we have just input x. So given target vector t and the data matrix x, then we want to identify the best parameters for a regression function like this. And the solution is given by this. This one is coming from the previous slide, right? So instead of using phi, we just use x. Okay. And it is a maximum likelihood estimate with an assumption of Gaussian noise, or it is a empirical risk minimization with an assumption of squared error. Okay, so we already talked about these two things from the previous slides. Okay, and then extension of a basis function gives expression power. So basically the equations are the same. Okay, so in this simplest form, we just use identity function. So the basis function is just the identity. Okay, otherwise, if we can come up with really nice nonlinear function, then we can improve the performance, or we can increase the expression power based on the basis function. Okay, and before talk about the special algorithms, then I want to talk about this regression function y of x, okay, in terms of this expected squared loss. So when we minimize the expected squared loss, the optimal prediction of a new x is the conditional mean of t. So it means, we have lots of samples, we have lots of training samples here. Then x naught is our new sample. Then what is the prediction, or what is the estimate of the output? In that case, if we have lots of samples here in the training samples, then we have lots of labels too, right? So we have lots of samples and labels, and all these labels might be different. Okay, so we have x10 here, x12 here, and x13 here. Okay, so we have 3 points here, but t10 might be 11 and t12 might be 11.2, t13 might be 10.3. Okay, then when we have a new sample here, then simply just average of these labels would be the output of this estimation. That's what this line says. Okay, so we can just prove what we just said. Okay, so expectation of loss is this. So this is our loss, and we multiply probability and the integral so that we can get this expectation of loss. Okay, then we're interested in y, so we just take derivative, then we set it to 0. Okay, then we can rearrange these equations, and y of x is independent of t, so this one is y of x and integral ptx dt, and this one is a marginalization, so this one is simply p of x. So y of x is, this one is the numerator and the p of x is the denominator. Okay, then look at this one. This one and this one will be this conditional probability. So the output of x is actually the expectation of t given x. So this slide says really trivial things. We all know this is trivial, so we know this, but we just use the equations to make it, look complicated. Okay, so you already know this. You usually this kind of common sense in your daily lives, but we just use the equation.